All right, so here we go. We're going to start the next video on insurance calculations and games of chance calculations and see how expected value is done in that realm. So let's start out with an insurance example. Um, Here it says an insurance company insures farm ground for $300 per acre if the ground is destroyed and the crop doesn't come in. The probability that the farm ground is destroyed is 1 in 120. The company charges $8 per acre to insure crops. Find the expected payout and the expected profit for the insurance company. Now, before we actually get into the problem, let me talk about what insurance is actually doing. So we're going to make a very, very crude sketch here and talk about what the insurance company is doing. So let's pretend we draw a farmer, and I'm just going to draw obviously a stick figure for the farmer. Boom. Well, what the insurance company is going to do, we'll represent the insurance company by some big block, big blue box. So here's the insurance company, okay? Now, what we're saying about this is that the farmer, when it says pay a premium of $8, we're saying the farmer pays $8 in no matter what happens to the farm ground. So he's paying in $8 or she's paying in $8 to insure the farm ground. Now the insurance company actually has two options in order to pay the farmer. Option one is going to be the ground is destroyed. And we see that if the ground is destroyed, what the insurance company has to pay the farmer is $300. Now, in reality, insurance companies often pay anything between up to $300. So there's always some sort of adjustment level. But let's just, for the sake of argument, and the sake of this problem, and the sake of the chapter, say the ground is either destroyed or it's safe. So if the ground is destroyed, the insurance company pays the farmer $300. If the ground is safe, if there's no disaster, the insurance company doesn't pay any. Now, if we think about what this means in terms of profit and loss and payouts, well, in terms of profit, if the ground is safe, in other words, if the insurance company has to pay $0, then the insurance company made $8. If the ground is destroyed, well, the insurance company is losing money. They're going to get in $8, but they're going to have to pay out $300. Okay? So the idea of this comes down to, well, those two options of paying out $300 versus paying out $0 are two options that could happen, but they don't have equal likelihood. Obviously, we see here that the probability that the farm ground is destroyed is 1 in 120. So what does this mean? This means that we can create a probability distribution for the expected payout of the insurance company. So when I say the expected payout, I'm just saying this bottom part of the picture. When we get into the profit, then we'll tack on this $8, this guaranteed $8. So let's take a look at this. What I would do to create an expected payout is I would first create a table. Okay? Now, my table is going to be a little bit bigger than necessary, but that's okay. What I'm actually going to do is I'm going to start the table right here. So payout, let's just call the variable y for payout. Okay, sometimes people will use different letters as needed. So we understand that a probability distribution, let's ignore this top row, is going to list out all of the possible payouts along with their probabilities. So the possible payouts we just saw are $300 or $0. Now that $300 is if the ground is destroyed. Again, I'm just putting this above there. Maybe you would not like to see those. Let's actually make it a little bit easier. Let's just do a standard probability distribution. So if the ground is destroyed, the farmer, he or she, gets $300. If the ground is safe, that payout, and again, that when I say payout, we're talking about the amount of money that the insurance company pays out, is going to be 0. Okay? Now, we see that the chance that it is destroyed is 1 in 120, 1 over 120. And actually, let me do this as a fraction that way. Now, what's the probability that the ground is safe? Well, clearly, because of the properties of probability distributions, we know all of the outcomes are listed, so the probabilities have to add to 1. So since they have to add to 1, this one has to be the leftovers. It has to be 119 out of 120. In other words, in this case, it has to be the complement of, so safe is the complement of destroyed. So now we can deal with calculating the expected value. And when I say expected value, I'm talking about the expected payout. So we're talking about E sub y in notationally. So we're going E sub y, E of y, expected payout is going to be, well, if we want to put this into our calculator, we can. We can put y in the outcomes in list 1, the probabilities in list 2, and then do one variable stats and get the average. But it's probably easier in this case because we have so few options to just take 300 and multiply it times 1 over 120. And then add it to 0 times 119 over 120. Okay, so that's the rule we figured out last time in the last video. If you want to go back and check that, that's fine. Just take the outcome, multiply it times its probability, outcome, multiply it times its probability, and then add them up. It's really nice in this case since we're dealing with zeros. Whenever you're dealing with zeros, it's kind of nice. So 0 times, again, that's not a very good time symbol, but let me just write it normally. So 300 times 1 over 120 plus 0 over 119 over 120. So what we find is that the expected payout, remember we said payout was our y, is actually 2.5. And that comes, if we're talking about dollar amounts, $2.50. So we set up a probability distribution based on the word problem, and then we calculate it. We get expected payout is 250. Now, again, think about what that means in terms of this picture. That means on average, the company is paying out $2.50 per every farmer. If you remember, this is the point of where statistics is important. Remember what that means. That does not mean every farmer gets $2.50. What that means is if some farmers are going to get 300, lots of farmers are going to get 0 in this scenario. But when you collect all those, add up all those payments, and then distribute those equally distributed add up to about $2.50 per person. And so $2.50 worth of payout per person. Now, when you go to find a profit, we could create another probability distribution if we wanted to, but it's easier to think of the profit as saying, well, the insurance company is going to pay out $2.50 on average. How much are they going to get for every acre? Well, they're guaranteed to get $8. So the expected profit is going to be just the difference. They're going to get $8, but on average, they spend $2.50. So their expected profit is the difference between those, which is $5.50. So the insurance company is going to profit on average $5.50 per acre that they insure like this. Okay? And this is how the insurance companies make money. Yes, they know that some of the ground is going to be destroyed. They also know that some of the ground, most of the ground is going to be safe. But they know when they insure lots and lots and lots of farmers, it's going to average out to making a profit. So that's how insurance company works. That's how makes money overall. So they don't make money on every single individual, but they know that if they insure enough people, they're going to make money over the long run. All right. I want you to try. Oops. Example 3 on your own. I want you to read this and I want you to be very careful to read this, create a probability distribution for the expected payout, and then use that to find the expected profit too. I'll pause the video. I'll wait about 5 seconds and then explain it. All right, so in this case, insurance company insures a person for $1.5 million if the person is abducted by aliens. By the way, you can find these weird insurance coverages on the internet sometimes. That's what this came from. Now, to get this insurance, the person has to pay a premium of $150. So basically, they pay in $150. That's like the $8 we had last time. And then they get out 1.5 million if the person is abducted by aliens. Now, we all know, hopefully, that we're not going to get abducted by aliens. But let's just pretend the chance that a person getting abducted by an alien is 1 in a million. So what's the insurance company's expected payout, and what's the insurance company's expected profit in this case? All right, so let's create our probability distribution. Our probability distribution is going to look like this. We're going to create a table. And again, there's not very many scenarios here as far as payout goes. We're only going to have 2 options. You're either going to be abducted, or the more likely scenario, you don't get abducted by aliens. All right? So in terms of payouts, I'm going to make this a little bit bigger. In terms of payouts, if you get abducted by aliens, it said they're going to pay 1.5 million. Now that's that number. Make sure that when you're doing this, don't just put 1.5 in there. Actually put 1.5 million as a whole number. And obviously, if you get nothing if you're not abducted. Now, what are the probabilities in each scenario? We jokingly a little bit said that 1 in a million is the chance that you get abducted by aliens. Again, that's probably very, very high. And the chance that you don't get abducted by aliens would be 999,999. 999 out of a million. So we can go ahead and calculate the expected payout by taking expected payout. Again, I'm using Y for payout. You can use whatever letter you want. I don't mind, actually. Excuse me. Oops, sorry about that. Let's go 1.5 million multiplied times 1 over, 1 million, and then plus 0 multiplied times 999,999 out of a million. Usually that takes me a little bit less time to write on the board when I do it on the board. Okay? So what we see there, again, this is just the standard rule for how to find an average or expected value. What we see is that the expected payout is going to be about 1.5, and that's it, just 1.5. So $1.50. Okay? Now think about what that means in terms of profit. If the actual chance of being abducted by an alien was 1 in a million, your expected profit would be, well, you have to pay a premium of $150. So we're going to take 150 minus, on average, you pay out $1.50. And what you're getting is that your expected profit is $148.50. So there's a pretty good return on investment if you're insuring people for being abducted by aliens. Now, again, this scenario is a little bit silly, but people actually buy some really, really weird insurances. So while it's a little bit silly, it's probably not, I mean, it's a thing that actually exists, and you can look that up on the slides, or excuse me, through this website that I cited there. Okay. Now, here's another one. The last two problems, the probability of the farm ground being destroyed and the probability of being abducted by aliens was given to me within the problem. Okay? In this problem, this one's a little bit more realistic, but we're not given a probability. So let's go through this one. I'll do this one right now. Assume we work at an insurance company, and an average 22-year-old male walks in and says they want to buy life insurance. And they're only going to buy life insurance for 1 year. We'll make it easy. We'll do it by single years. And they're going to want to be paid $300,000 if they die. Now, hopefully, we all are mature enough to understand how life insurance works, right? So basically, you pay the insurance company a premium, and the insurance company, if you lived, is not going to pay your family anything. But in the chance that you die, the insurance company is going to pay your family whatever that amount is. In this case, the insurance company would have to pay the average 22-year-old male's family $300,000. Okay? So what we're going to do is we're going to calculate how much the expected payout would be. And then we're going to say, well, insurance is actually a pretty life insurance is pretty competitive. There's a lot of places that sell life insurance. And so we're not going to be able to mark it up like we did the alien abduction insurance, right? We had a huge profit on that. Let's assume that what I want to do is I want to calculate this guy's payout, the expected payout, excuse me, and then charge him an additional 10%. And that additional 10% that I charge on top of the payout is going to be like profit for the company. And that'll go to, all of the expenses and things like that. So most of the table for an expected payout can be actually created by just taking the same steps we did last time. Let's take another. There we go. So here's what we're going to do. Let's create another table. And this one's really easy in terms of options. What's the payout? And what's the probability of those payouts? Well, what are the two scenarios? Basically, the scenarios are the person either dies or the person lives. Okay? Now, if they die, we see that their family is going to receive $300,000. That's how insurance works. And if they live through the year, they get 0. Okay? Now, here's where things start to get interesting. What is the probability that an average 22-year-old male would live through the year? Well, that's not something you and I could figure out in our head. What happens, though, is these insurance companies will collect some empirical data, right? And they'll use empirical probabilities to determine the probability that that person lives through the year or dies within the year. Now, we don't have access to the insurance company's records, and most of those probabilities are pretty specific. But what we do have is something called a Social Security actuarial life table. All right? So, oops, I misspelled actuarial when And you can see these, again, by just Googling Social Security actuarial life table. Click on something like that, and here is the Social Security's actuarial life table. Now, this one is for 2015. You could do it for other years if you'd like. Let me take a moment to talk about what this is telling us. So what the Social Security Administration does is they collect records on, how often people are dying and those types of things. And they break it down by two categories. First, male versus female, so the sex of whoever's living, and then by their age. All right? So what we would do for the 22-year-old male is we'd scroll down to 22. Males in this table come first, and we see that there are 3 numbers here. Now, this number here is the probability that they die within the year. So, in terms of exact age, people who are just born, males, their chance of dying between birth and year 1 is 0.006383. All right? Notice that's actually a lot higher than the chance that they die between year 1 and year 2. That's actually 0.000453. So this probability, although it's very low, it's actually a lot more than there. Again, a lot of times infants can be born with some really bad complications and things like that. The same thing is true for females. We can look at the probability of dying between age 0 and age 1, and so on and so forth. So let's say this average 22-year-old walks in, and we look at this probability of death. By the way, I'll explain these two numbers in just a minute. So that's the probability that that 22-year-old dies within the year, 0.001339. So we go to our table and we say, well, the probability is 0.001339. Let me actually double check that, make sure I got that right, 0.001339. Now, just like we did before, we only have two options. Since they have to add to 1, this has to be the complement. So I'm going to take 1 minus 0.001339, and the complement is 0.998661. Now, by the way, one thing you'll notice here is that I went out to more decimals than I usually do. On the test or something, I'd probably go out to 4 decimals, but since we're doing this and we're looking at the actual actuarial life table, I'll take those probabilities out to whatever the actuarial life table gives me. And in this case, they go out to 6 decimal places. So again, normally I'd round to 4, but we'll take them out to 6 because that's what the actuarial life table does to us. Okay? And so now we can easily calculate the expected payout in the exact same way we've been doing this whole time. So $300,000 times 0.001339 plus $0 times 0.998661. All right. And if we do that, 300,000 times 0.001339, I got 401.7. So the expected payout is, in this case, 401.7, $401.70. Hopefully I calculated all that stuff right. I did it fairly quickly into my, put that fairly quickly into my calculator. All right, so that's the expected payout. So what does that mean? That means that if lots and lots and lots of 22-year-old males start walking in, if they charge everybody $401, excuse me, on average, the insurance company should pay out about $401.70. Now, what should they charge? They're going to charge 10% more than what they already have. So they're charging 10% more than the $401.70. Hopefully, we all know how to do this. When it says charge 10% more, that means they're going to charge 110% of that number. And 110% is 1.10 multiplied times that number. Okay? So they're actually going to charge $441.87. Okay, so they're charging 10% more, which 10% more comes up to $441.87. All right, again, I round that to 2 decimal places. This one came out nice and even at 2 decimal places, but I'd round it to 2 decimal places if I didn't have other options, or if I had more decimals, excuse me. Okay, so hopefully that makes sense, that now what we can do is we can put ourselves in the shoes of the life insurance company, and we can say, well, an average 22-year-old male walks in. Now I know what to charge them. Okay? Now I know what to charge them. Now, here's one thing well, a couple of things that you'll notice about this actuarial life table. First off, the, excuse me, the probabilities, and I know I'm scrolling through these fairly quickly, but the probabilities of dying if you're a male are actually higher than the probabilities of dying if you're a female for, I believe, about every age. There might be one age that's different, but I think that, yeah, for every single age, the probability is actually higher of dying if you're a male. So even at birth, males have higher death rates than females do. Okay? These are, again, children who were born. So at every single age, males are more likely to die. Now, how that would translate into an actual problem is it turns out that this number, how much you charge, would be decreased if I said the average 22-year-old female walks in. All right? It turns out, again, since males have higher death rates than females, uh, in general, you could charge females less because they're less likely to die. And that probability of dying being lower is going to lower the expected value. So again, if there's a husband and wife combo and they both go in and they both buy $300,000 worth of life insurance for the year and they're the same age, they're probably going to charge the female a little bit less. All right? See, that's I don't know. That's just the way things go, all right? And by the way, this is not, hopefully we're all smart enough to say, this is not because death is sexist. This is just the numbers. This is how the numbers break down. All right? That would be really stupid, wouldn't it? Say death is sexist against males? Yeah, that'd be kind of a dumb thing to say. So that's one thing you see, that females and males have different numbers, and also you'll notice that when you're really young, again, 0 has a fairly high death probability, but it starts going down up until about the age of 10, and then after the age of 10, it starts going back up, the probability of dying. And once you get into the really high age groups, your probability of dying that year becomes pretty high, right? If you get to the age of 95, you have about a 26% chance, 27% chance of dying if you're a male, about a 22% chance of dying if you're female, okay? So all of that is to say that um, probabilities, these probabilities of dying are going to affect how likely, well, let me put it this way. The probabilities of dying, because they're embedded in this formula here, if I take a lower probability, the payout's going to be lower. If that probability goes up, the payout's going to be higher. And that's going to determine how much that insurance company charges you. So it's not some sort of a weird conspiracy thing about how much the insurance charges you. They're just charging you a certain percentage more than what they think your expected payout is. All right, that works also in terms of medicine, health coverage. That works also in terms of, that works also in terms of car insurance, things like that. Okay. The other thing that I was going to point out is that I keep saying average 22-year-old male, and I do want to just make a note to say what this number represents is actually the probability of death for all 22-year-old males. So we're not talking about probably you if you're 22 years old. This number would include people who are sick, people who are on their deathbeds. This number would also include people in really high risk, high um, high death professions. That's some of the reason why the probability of dying is higher if you're male, because it tends to be males take on those jobs that are more high risk, more of a high risk of dying and those types of things. Um, but again, that number would probably be that probability of you dying this year would probably be even less than that if you were a healthy 22-year-old male who worked in, retail or something like this, or worked in um, at a college or things like that. So don't expect that this actual life table is really reflective of you if you are a 22-year-old male. All right. Or the same thing if you're a 22-year-old female. Don't assume that that number fits you perfectly. It's probably lower than that. Oh, one last thing I wanted to point out. Now I have to go back to the actuarial life table. Okay. These other two columns, basically what they represent is the life expectancy at that point. So at birth age, men in 2015 had a life expectancy of 76.15 years. All right. Now, if you go down, why these numbers are going down? Because if you get to age 6, the life expectancy is 70.73 additional years. Okay, so if you add up 6 plus that, 76.73, you have a slightly higher life expectancy the longer you live. All right, because obviously you didn't get killed in these groups. And this middle column here for both the females and males is if we start out at 100,000 people born, let's say today, and then 1 year from now, this is about how many you would expect to remain. All right. And then a year from that, 2 years down the road, this is how many females you'd expect to remain. And if you do this and you do the probabilities, what you'll see is as you start getting up into older and older ages, what's happening? Well, there's a lot more females who live to be 98 than are males who live to be 98. Okay, so that's kind of what's happening. And if you go up into the 100s, 42 males left compared to 184 females who are left. All right, so those are the other two columns. Again, that's not anything to do with the things we're doing today, but it does explain some of that actuarial life table. So let's do this. Let's sort of start transitioning from insurance to actually betting, okay? And we're going to do this in the most bullish way. I don't know, the most crude way possible. Because if we think about it, life insurance in some ways is kind of like betting on your own death. So all we're going to do is switch the scenario. Instead of betting on your own death using life insurance, let's bet on whether or not some famous person will die. Okay? And so I'm going to create a casino which bets on whether or not some famous people die. And we'll have a bunch of different people at this casino that you can bet on. And it's always going to be a bet like, will they die within the year? So somebody puts money down and they'll pick a famous person. And if they bet within, if they, excuse me, if they die, if that famous person dies within the year, they win the money. If that famous person lives, then they lose the money. Okay. Now we'll once again use the actuarial life table. And let's assume that the expected payout is $100 in case the celebrity dies. How much money would we have to ask the bettor to put down in order to actually make money on average? So let's go ahead and pick a celebrity. And this is actually something that people a little bit morbidly do. But here's one such a list of celebrities. Now, I will say this. The actual placing money on other people's deaths is illegal in the United States. So don't go ahead and do this. But people do talk about this and they rank um, which celebrities are going to die next and all that kind of, again, a little bit morbid thing. But you can see some of these. Um, and again, I'm right now at February 5th, 2019. So hopefully, as you're seeing this, some of these haven't passed away. Although I see Carol Channing did, in fact, die this year. So let's take, I don't know, let's take Robert Mugabe. All right. He is the current president of Zimbabwe and not the greatest of person. There's all kinds of, he's been really kind of ran Zimbabwe into the dumps. But yeah, I don't see any other doozies. So we'll take Robert Mugabe. Where was he at? You can see some of these others. He's up there. Okay, so Robert Mugabe is 94. All right. So if I wanted to somehow create a bet on Robert Mugabe, what would I do? I would do the exact same thing I did with the insurance company. I would go up here, create a table, and again, just like the insurance company, he's either going to live or excuse me, just like life insurance, how you live or die, same thing with Robert Mugabe. Now, we're going to say payouts is $100 if he dies and $0 if he lives. So we create this. Robert Mugabe dies and Robert Mugabe lives. Again, hopefully this is not too morbid once you see this, but maybe Robert Mugabe is dead by the time you watch the video. Who knows? All right. So, like I said, Robert Mugabe is 94. We're going to assume he is the typical 94-year-old male. We'll go back to our Social Security life table, and we'll scroll down to 94-year-old males, and their probability of dying is 0.244094. Okay, right there. So that's the probability, 0.244094, that we're going to use. And obviously the other probability, the probability that he lives, is 0.755906. Now, one thing you'll probably start noticing is that every time I calculate the expected payout, really this first multiplication is the only one that's actually going to matter. Because that second multiplication, anything multiplied by 0 is just going to be 0. So when I take and multiply, and again, I'm just plugging that into my calculator, I got that the expected payout, the average payout here, theoretical average, was $24, whoops, and 41 cents. Okay? So what does that mean? That means on average, if I did this for lots and lots of celebrities on that list who are all 94 years old, some of them are obviously going to pass away, some of them are not. But if you did this over and over and over, it would cost you about $24.41. It costs the casino that you're setting up $24.41 per bet. Um, so what would you do? Well, as the casino, you would just make sure that you charged more than $24.41. Maybe you charge $40 to make that bet, or maybe you charge $50 to make that bet, depending on how much you wanted to make. Or maybe if it's a competitive market like life insurance is, maybe you charge 10% more, like we did. Okay? So notice that the actual mechanics of the death bet is the exact same as the mechanics of life insurance. Okay? So numerically speaking, these two scenarios are basically exactly the same. Now, obviously, morally, they're different. Legally, they're different. You cannot legally bet on celebrities dying. I'm pretty sure you can't do that. But you can obviously take out a life insurance policy, and lots of people do. So the point is, we still are creating a probability distribution. We're still calculating our expected payout in the exact same way. All right. So let's go on to another example. Maybe I'll project this one up through the PowerPoint slide. Let's go on to example 6. So here's the situation. We're going to hold a lottery. And when I say hold a lottery, basically think of scratch-off tickets. We're going to have a roll of 10,000 scratch-off tickets, and we're going to sell them at $1 a piece. Now, amongst these 10,000 tickets, 5 of them hold prizes that are worth $1,000. 30 of these tickets have prizes that are worth $100 a piece, and 50 of the tickets have prizes that are worth $10 a piece. And then all of the other tickets are just scratch off, you don't win anything. So we're going to find the expected payout if a person buys a ticket in this scenario. So notice that right now, instead of that lottery example where we only had two different payouts, the insurance example where we have two different payouts, this lottery example has a lot of different payouts. So if we went back to our drawing, let me go back to this drawing and erase some of it. Instead of the insurance company, we'll call that the lottery. Man, that was longer than it took me to write that. So what are the options here? Well, now there are 4 different options of different payouts. We said some of the tickets have $1,000 prizes. Some of the tickets have $10 prizes. Some of the tickets have nothing, so on and so forth. And then obviously you're going to pay in to the lottery $1 every time you pay. I'm not going to write all those numbers because we don't need to do that right now. What we will do is we will set up a table. Okay, now the table I'm going to use needs to be big enough to have all of the different prize money amounts. So when we're dealing with this, I don't run out of room. So what are the different prize money amounts? What are the different payouts that I could get? Well, they said 5 prizes are worth $1,000 apiece. So $1,000, that's one of the payout options. We have 30 prizes that are worth $100. So $100 is another payout option. 50 prizes worth $10, that's another payout option. And then all the remaining tickets are worth 0. So here we have 4 different, again, payouts. And each of those is going to have an associated probability. Now, again, these first couple examples we did with expected value, the probabilities were just embedded into the problem. We saw in the next couple of examples that the probabilities we could look up on like an actuarial life table. Well, here we get the probabilities in the way we got them from chapter 3. We're going to use classical probability techniques to find these probabilities. Here's what I mean by that. Basically, we have 10,000 tickets, and 5 of those have the big prize. So what's the chance of getting one of those tickets with the big prize? Well, classical probability would say we have 5 chances out of a total of 10,000. So classical probability gives me that probability. Similarly, 30 of the prizes of the 10,000 are the $100 prizes. 50 of the prizes out of 10,000 are the $10 prizes, and the rest have nothing. Now, in this case, we have to be a little bit careful here. How many tickets in total did we use? We used 85 total tickets. 85 total tickets out of the 10,000. So what that means is the remaining 9,915 tickets have nothing on them. So the probability of having $0 is 9,915. And just like always, when we're doing this, what are we going to do? Expected payout. We're going to take each of these numbers, 1,000, and multiply it times their corresponding probabilities. And then add them all up. And I'm doing this, it takes a little bit of time to actually do all of the writing of it down. It takes a little less time to actually do this when you're actually writing it by hand. So that's what it looks like. Okay. Now, when it's all said and done, you're going to calculate that. By the way, this one is borderline. We have 4 options here. So maybe you might want to put it in your calculator again too. Remember, you can always do this on your calculator by putting the payout options in list 1 and their corresponding probabilities in list 2. So expected payout you would get by finding the average with either on, again, on your calculator you could do it, list 1 all the y's, list 2 the probabilities, or you could do it by hand like I'm doing it right here. But in the end of it, we're going to end up with the expected payout of 0.85. So in other words, 85 cents. Now, what does that mean? what that means is that for each dollar you spend, on average, you get back 85 cents. Now, is that a good deal? Obviously not, okay? This is a game that over time, if you continually play it, you're going to keep losing 15 cents for every dollar you play. Okay? So this lottery, if you keep playing it, you are going to lose money. And if obviously the states or whoever's doing the selling of the lottery tickets, if they keep playing, they keep winning money, again, on average, because they're not just selling one ticket. They're selling all 10,000 of these tickets. And when they sell all 10,000 of these tickets, they make about 15 cents per ticket. And if you add that up, 15 cents per ticket, they're making about $1,500. Okay. Now, actually, as far as lottery goes, that's actually probably a high payout on a lottery ticket. Okay, they're probably actually making more than that in general, but on these scratch-off tickets. So if you go into the scratch-off tickets, they're probably making more in general. There's probably also a lot more of these prizes that I haven't listed yet. Okay, so there you go. That's how the lottery works. That's what happens when you create more and more outcomes for payouts. Again, this is the first time we had multiple different outcomes for payouts. Now, what I would like you to do, well, actually, let me do this one, and then I'll let you do the next one on your own. So here's what we're going to do. We're going to do a very similar thing. We're going to play a dice game like craps, where we roll 2 dice, and then we're going to get paid on some of the outcomes, and we're going to not get paid on some of the other outcomes. Okay? Now, in chapter 3, we saw how, or maybe in the previous section, we saw how dice add and how to calculate how dice add together. All right? So what's happening here is we're going to have a few different options for payouts. If the dice add to 2 or 12, then the player is going to get paid $6. If the dice add to 7, so if your person rolls a 7, then the player is going to get paid $2. And then it says the game is going to cost $1 to play. So in other words, I'm going to pay the dollar. If the dice add to 2 or 12, I get 6. So I'll get my dollar plus 5 more back. If a person rolls a 7, then I get $2. So I get my dollar plus an extra dollar. So we're going to find the expected profit of the game and then ask ourselves if we should play the game. All right, so we're going to do this in the exact same way. Now, if you think about it, what's going to happen in this table? There's going to end up being 3 different options for payouts. So we're going to take this table and we're going to give 3 different options for the payouts. Now, why 3 different options? Well, basically you can get paid $6, you can get paid $2, or there's also the option of 0, okay? The $1 is just how much it costs to play the game, okay? So if we look at the expected profit, we're only going to deal with these 3 different payouts. Now, how are we going to find these probabilities? Well, basically remember that a 6 meant we're going to roll a 2 or a 12. And a 2 meant that we were going to roll a 7. And a 0 is basically anything else. All right, so let's go ahead and calculate rolling a 2 or a 12. Now remember, there's a couple of ways to do this. I could draw my 6x6 grid. We've done that in the past. But what I'm going to do is I'm just going to look back at our notes. And looking back at our notes, we had this probability distribution where x was the number of the two dice, of the sum of the two dice, and then the probabilities were here below it. So rolling a 2 or a 12, we see our first option is a 2, our last option is a 12. So 1 in 36 chance of getting a 12, a 1 in 36 chance of getting a 2. That means that it's a 2 in 36 chance of getting either a 2 or a 12. Rolling a 7, we see there's a 6 in 36 chance. So that's all we have to do. We have to look at something like that, or again, check out that 6x6 grid and figure it out based off that 6x6 grid that we drew in the last video. So rolling a 2 or a 12 has a 2 out of 36 chance. Rolling a 7, well, that had a 6 out of 36 chance. Anything else? Well, instead of adding all those other probabilities, what I'm going to do is I'm just going to realize that this accounted for 8 out of the 36 slots. So we have 28 out of the 36 slots that are unaccounted for. Okay? And then once again, the same standard technique. We're going to say if we want to use our calculator, use your calculator. List 1 is the payouts. List 2 is the probabilities. Or we can find the expected payout. Again, I keep using Y for payout. You can use whatever letter you want. We're going to do the expected payout, though, of 6 times 2 over 36 plus 2 times 6 out of 36 plus 0 times 28 out of 36. All right. And when we do that, we get an expected payout, which is, oh, whoops. I calculated that incorrectly. Rounded to 2 decimal places, 0.67. Okay, so about 67 cents is the payout. Now think about this. If the game costs $1 to play, how much profit is there? The expected profit, we haven't done this in a minute, is 1 minus 0.67. So the expected profit is actually 33 cents. Now, when I say expected profit, we're talking about the expected profit for the casino, not for the person playing. Okay, the expected profit for the person playing would be negative 33 cents. So it depends on what, which way you look at it. But profit, the person who wants to play the game, who's paying the dollar, is losing 33 cents for every dollar they play on average. Okay, so that's how that is done. Now, obviously, if I ask, should you play the game? Should you be the person putting the dollar in? I hope that we all can conclude, based on this data, that no, this is not a good game to play. You're losing 33 cents every dollar you put down. So it would be an unwise game to play. And actually, if you look at all the casino games, this would actually be really bad to play. Okay, most casino games have an expected payout, if you play them like perfectly, of close to $1. Again, if you play $1, it's about close to $1, but it's still in the casino's favor. So still, it's a bad idea to put all your money into the casino. Now, again, if you're wanting to go there and have fun or something like that, that's fine, but don't think that you're going to get rich playing games at the casino. Don't think that that's a good, wise retirement strategy. That's not what it is. So here's what I'll do. I want you to try example 8 on your own. This is the last example of section 4.1 of the notes. So push pause, try this example here. All right, hopefully you did that. So same concept, still having players roll 2 dice. Now we're just adding different numbers in. If the sum is 6 or 8, then the player wins $3. If the person rolls a 7, then they win $1, and the game costs $1 to play. So let's go back to notes. Again, notice that I'm going to get to a new page there. I wouldn't normally do that if I were writing this down by hand, but it's a little bit easier to deal with a new page in here. So again, three different payouts. Okay, we have a $3 payout. Whoops. If the person rolls a 6 or an 8, we have a $1 payout if the person rolls a 7, and then we assumedly have a $0 payout for anything else. So we have 3 different payouts. There they are. Okay. Let's scroll here. Roll 6 or 8. Roll 7. Or anything else. All right. Perfect. So scrolling back to that probability distribution example and finding the probabilities, we see that a 6 or an 8, a 6 has 5 of the 36 possibilities, an 8 has 5 out of 36 possibilities. So together, they'd have 10 out of 36 possibilities. The 7 would have 6 out of 36 possibilities, and then we can calculate the rest from there. So what is the probability of each of these different payouts? Well, a 6 or an 8, what I just say? 10 out of 36. A 7, I just said that 6 out of 36. Now that's a total of 16 possibilities out of 36. So the remaining 20 possibilities out of 36 give you a result of $0. All right, I'm going to extend that out just slightly. And now we're back to our standard technique. Again, if we want to, we can go expected payout or expected, I could put a Y there if I wanted to, equals 3 times 10 over 36 plus 1 times 6 over 36 plus 0 times 20 out of 36, which actually comes up, weirdly enough, to exactly $1. All right? And if we say, well, we just said the game cost $1 to play, so what is the expected profit of this game? And you say, well, 1 minus 1 is just 0, so $0. So what this means is if you just keep playing over and over and over this game, you're probably going to break even, or at least come very, very close to breaking even. Again, if you play it enough times. This is what's known as a fair game. Okay, so this game is what's called fair. That the player and the casino have an equal chance of actually winning if the casino had this game. Now, obviously, this game is never going to be found at any casino because the casino is not going to want a fair game. They want a game that's slightly tilted towards them. Oddly enough, they don't want a game that's super heavily tilted towards them. They want a game that's slightly tilted towards them. Because if it's slightly tilted towards them, even though they're winning more times than they're losing, players often will want to win enough. Like if you sat down and you lost 20 hands in a row before you won one, then it's going to be a little bit discouraging. But if you win one and then lose one and then win a couple and then lose three and then win two and then lose three again, all of a sudden it doesn't feel like you're losing as much money. So actually they want you to win some so that you can keep playing, and as you keep playing over and over and over and over again, they're going to take your money slowly but surely. All right. So that is what 4.1 is all about. It's creating these probability distributions and using them to find expected payouts. And then that allows us to make decisions like saying, hey, now that we see the numbers, probably shouldn't play those casino games. Probably now we can understand what goes into the life insurance calculations that you're getting or your health insurance calculations or whatever. Okay, it's not a big, vast conspiracy. It's just that those are the numbers. Okay. Now, one last thing before we close out. You'll notice that in every example we did in this video, we had created a probability distribution and then we used it to find the expected payout or the expected profit. One time we found out how much you charge. Well, on the test, I expect you to create a probability distribution. And even though that like the zero doesn't actually contribute much when we calculate the expected payout this way, still include the zero option every time. Okay, so when I'll ask you to create a probability distribution, which just means this table. Okay, you can draw it by hand, and it's a fairly easy thing to do, and then calculate the expected payout or the expected profit, or calculate how much to charge. But I do want you, every time you create this probability distribution, for payouts, do include the number 0. By the way, notice that I did everything with payouts. I didn't create any probability distributions with profits. That's on purpose. It turns out profits are a little bit weirder to deal with and a little bit more complex. Nothing's really that complex. But if we had to change this from payout to profit, we'd have to reduce all of these numbers by 1. So you'd have some positives, some negatives, and it's a little bit more confusing than just dealing with everything with payouts. Okay, so that ends chapter 4.1, and we'll start in on a couple of different ways to get probabilities next time. We saw that we got these probabilities using classical probabilities. We got these probabilities for our death bet and our life insurance using an actuarial table. We got these probabilities by just having those probabilities given to us. And so we'll do some other finding probabilities in the back half of chapter 4, and then some clever ways with those examples of how to find expected values and such. So this ends this video, and we'll start 4.2 video next time.